we have looked at transmission photoelasticity elaborately. Then we also had an idea of how photoelasticity can be applied for 3-dimensional problems. Then we moved on and looked at what way we can use digital image processing techniques to automate photoelastic analysis. Now we take up the industrial application of photoelasticity that has become a success with the advancements in photoelastic coatings. And what you have here is, I have the basic optical arrangement that is used, and once you come to photoelastic coatings, you need to make idealizations on how do you translate the results seen on a coating to the specimen. And one of the important factors there is to consider what are known as correction factors, which will improve your prediction of the results. And this shows a example of how the fringe patterns appear in photoelastic coating, and this also shows on a specimen I have a birefringent coating pasted onto it. And if you look at any of the techniques, we need to look at history behind it, and what you have as historical development. We have Messner in 1930 used segments of glass as a coating. It is very surprising, we have looked at in photoelastic materials that glass is also a photoelastic material, and it has a Poisson, it has a Young's modulus of 70 GPa equivalent to aluminum, whereas all other plastics we had only 3 GPa. And because this has a very high value of Young's modulus, one of the problems with glass was that it reinforces the specimen significantly. And after glass, what they tried? Opel in 1937 used flat sheets of bakelite. So, when we graduate from transmission photoelasticity to photoelastic coating, initially people concentrated only on flat surfaces. So, they initially used glass, which was found to reinforce the specimen significantly. The problem with bakelite was it has a significant time edge effect, and we have already seen in transmission photoelasticity, because of time edge effect you have spurious fringes that are formed. So, you do not want spurious fringes. So, bakelite was also not a suitable material when you want to go in for photoelastic coatings. And I said any development in science or engineering was always tagged on to developments in material science. So, what you find was availability of epoxy resins in 1950s contributed significantly to the development of the technique. So, it is a material research which has helped in advancement of photoelastic coatings. This has multiple names, you can call it as photoelastic coating, you can call it as a birefringent coating based on what is the kind of material that you use, and because you see the reflected light, this is also termed as reflection photoelasticity. And the other difficulty was lack of proper adhesives to bond these coating were also a problem. So, the development of the technique hinges on development of proper adhesives and also development of epoxy resins. Initially, many of these applications were confined to flat surfaces. Later, it was shown by Zandman, who developed in 1960 a unique procedure for preparing contourable plastic. See, if you look at any of the industrial component, you have a very complicated surface, and if I have to put a coating on top of it, I must be able to make the contour of the actual object. So, in a contourable plastic, the technology is you cast a sheet, and when it is in a gel state you take it out from the casting pane and then put it on the actual prototype, and then allow it to take the shape of the actual object, and in this process no stresses are introduced, because the plastic, the whatever the polymer that you use is in a gel state, it easily forms the contour of the actual object. After it is cured about 24 hours, you get as a shell, and this shell is pasted on the actual object and do the experiment. So, this was a very significant development whatever Zandman has introduced, and this is a very famous contourable plastic. And now you have whatever the sheet in a gel state is put with proper icing, and then you have such gel sheets available. You directly buy the sheet from them, take it from the cold storage and contour it. You do not even have to cast it and then wait for whether it has reached a gel state or not. All that your steps are simplified. You have those sheets available, but it is expensive. In abroad it is available, in India it has still not come. So, if you want to take photoelasticity to solve industrial problems, photoelastic coating paved the way, and particularly contourable plastic has made this technique very attractive. And the moment you come to any of the coating techniques, you will also have to study the problem of reinforcement. Whether it is significant or not, we will have to find it out, caused by the, in this case, photoelastic coating, and Zandman provided correction factors for interpreting the fringe patterns for engineering use. And this applies to all the coating techniques. Suppose even if you look at a strain gauge, it can reinforce when the specimen size is comparable to the size of the strain gauge. I said in the case of electronic packaging, I cannot go and paste a strain gauge on the leg of those IC chips, because the sizes are comparable. On the other hand, a optical technique would definitely help in such situations. In the case of photoelastic coating, if I use glass, it has a very high Young's modulus and it is definitely going to reinforce. So, people dropped glass and now moved on to epoxy. Nevertheless, when you are having a coating, if the coating is thin enough, then we do not have to worry about. In photoelastic coatings, coating thickness of 3 millimeters are not uncommon. So, you are really talking about sufficient thickness. So, that you have to keep in mind. And you have to appreciate that this is an engineering tool, and I have said engineering means approximations, and approximations are made in the interpretation of the optical information recorded. We say that we want normal incidence in photoelasticity, and you would find because of industrial application even that is compromised to some extent. And what do you do? First you get the optical information. The optical response of the coating is initially related to the coating stresses. So, that is what you find out, because all the theory that we have developed in transmission photoelasticity are equally applicable in photoelastic coating with slight modifications, and those modifications you can easily figure it out. So, the focus what we are going to do is we will not spend much time on the optical aspect, we will spend much time on the mechanics aspect. We will initially look at how the optics information is translated, but we will essentially look at how do you find out the coating stresses, from coating stresses how do you find out the specimen stresses, what kind of approximations are needed in this kind of analysis, that is would be the focus. And in engineering, when you are actually making certain approximations, you always bring in a correction factor. So, that is why it is an engineering tool, that is why he said Zandman contributed contourable plastic as well as a methodology to develop correction factors, which take into account the thickness of the coating and also its possible reinforcement effect. Then what you have? The specimen stresses are determined from the coating stresses, and as I mentioned earlier, the analysis is improved by the use of appropriate correction factors. See, in transmission photoelasticity, we never even talked about correction factors. The marriage between physics and engineering so good in transmission photoelasticity, there is no need for correction factors. But in reflection photoelasticity, even for calibration, you need to bring in the correction factor. If you do not bring in the correction factor, your evaluation of the calibration constant itself can be erroneous. So, right from the optical arrangement even to calibration, and even if you want to find out the stress concentration factor, you have to do it very carefully in reflection photoelasticity. In transmission photoelasticity, you just find out the maximum fringe order on the horizontal diameter and find out the average fringe order, you take the ratio, your job is done. And I have said in all the coating techniques, Poisson's ratio plays its spoil sport. So, you have to accommodate the role of mismatch of Poisson ratio in photoelastic coating systematically. So, that you will see even in the evaluation of the stress concentration factor. So, you will always have to look at it is an engineering tool, you make approximations. Because you make approximations, you improve your results by employing appropriate correction factors. This is engineering, engineering always we do like that, we do not give up. See, if I am unable to solve the problem in all its totality, I do not give up, I at least bring in correction factors and make my result as acceptable as possible, because in design people want results with 50% accuracy, that is good enough, because they always have factor of safety, they have such factors which accounts for deficiency in the analysis. Only when people develop some finite element code, they really talk of 0.1% accuracy, 0.01% accuracy, experimentalists do not operate that way. Plus or minus 2% most cases people accept, 5%, 10% and even 50% are allowed, at least we know I am closer 50% to the result, because the problems what you handle are very complex. Even a very little information which is available with certain level of confidence can always go into your design calculations. And we will see what kind of approximations are made in photoelastic coatings. We will also look at the basic optical arrangements and just observe the animation. So, what I have here is I have the prototype here that is shown with the hatched line, and I have the coating that is pasted onto this. And in transmission photoelasticity, we always wanted a normal incidence. Suppose I want to have a normal incidence, the possible optical arrangement could have a partial mirror here, so that the light passes through the polarizer and then part of it goes and hits on the model, and whatever the light reflected, that comes out and reaches your eye through the analyzer. And what strikes you first? See, we looked at in the case of transmission photoelasticity, thickness of the model is a key parameter. Then we modified it when we moved on to 3-dimensional photoelasticity, we looked at as length of the light path, because depending on the size of the 3-dimensional model and the angle of incidence, I may have different lengths. The length is the one which is going to determine the retardation seen in that light path. So, if you look at what can immediately guess when I have a reflection arrangement like this? Very simple. Suppose I have thickness of the coating as HC, because light goes in and comes out, all those equations are equally valid if I replace thickness by 2HC, because the light actually travels twice the thickness of the coating. So, you get how transmission photoelastic equations could be translated into reflection photoelasticity. Though this optical arrangement is good enough for a plane polariscope, the use of a partial mirror affects the ellipticity of polarization when I use it for a circular polariscope. And not only this, an arrangement of this nature is large and cumbersome for portable use. If you really want to have normal incidence in reflection arrangement, you cannot avoid a partial mirror, and partial mirror is good enough for a plane polarized light, but in a general elliptical polarization it interferes to some extent on the state of polarization. This is one defect. The other defect is an arrangement like this is bulky, it is not efficient for you to carry it around and set it up in a industrial environment. So, what is the kind of arrangement that they have in a commercial reflection polariscope? Observe the animation again. So, what I have here is I have to send the ray of light to the model and I have to analyze only the reflected light. And what I can do this is, I have to do this at an angle for me to see the reflected light. The way I can improve my technique is keep this light source and your observation far away from the model. So, it is about at least 2 meters is what is recommended. When you have that kind of distance, this angle of oblique can be as small as possible. You do not want to have compromise fully on normal incidence. You do not want to impinge the light at 45 degrees, you do not want to do it that way. You want to have a shallow angle of oblique, and in order to achieve that you view the model from a distance. So, in the case of reflection photoelasticity, now people replace human eye with a camera. So, they use telephoto lens which will focus objects at a distance very conveniently, and by keeping the optical elements away from the model you reduce the angle of oblique, and this is of the order of about 4 degrees. The angle of oblique is usually of the order of 4 degrees, and what you find here, engineering approximations starts right from the data collection stage. And this set of optical elements can be put in a very convenient form, and you can even hold it on the hand, and you just need the light source and view the model. And you already know this P denotes polarizer, when I say Q1 it denotes the quarter wave plate 1 and you have the quarter wave plate 2 and you have the analyzer. So, in order to maintain the angle of oblique as small as possible, you keep your optical elements at least about 2 meters from the specimen surface, because if I get it very close then the angle of oblique will increase. So, I would like to have it as small as possible, and this is the optical arrangement of commercial reflection polariscopes. Many reflection polariscopes are available, and there again you can employ digital photoelastic analysis. And one of the outcome of this kind of approach is also what are known as photoelastic strain gauges. What they have done is, along with the coating, you will have the quarter wave plate and polarizer integrated with it. These were developed in Germany. Like you have electrical resistance strain gauges, you will have a small strip of plastic with its own quarter wave plate and polarizer embedded, and paste it on the model and view it in normal white light, you will see fringes. When the model is loaded, you will see fringes on the optical, it is a optical strain gauge, and it was popular for some time. So, the philosophy there is they just put a quarter wave plate and polarizer integrated with the coating, and you would see, and you will see the isochromatics. You will not see isoclinics in this arrangement. In those days when you have a uniaxial stress or biaxial stress, even that knowledge was considered important, and people had strain gauges, photoelastic strain gauge with a hole on it, and then they will find out whether it is uniaxial state of stress, biaxial state of stress. It gives you quick information, because in a strain gauge you have to connect it to an instrumentation and read the strain. Here, if there is any load applied, you will see movement of fringes. So, it was very attractive. So, the circular polarizer comes integrated with the birefringent material. So, what you look at now is, you have looked at, if I want normal incidence, what is the kind of optical arrangement I should think of in reflection photoelasticity. We saw that it requires a partial mirror. We said that it is bulky and also it interferes in ellipticity of polarization. So, it is not desirable to have that. So, we moved on to a commercial polariscope where we allowed certain angle of oblique, without which you cannot see the reflected light. So, you have to live with that, and but what you will have to look at is, what is the advantage of photoelastic coatings? The coating material is isotropic, the base material can be anything. It can be composite, it can be ceramic, it can be rubber, it can be bone, it can be aluminum, it can be steel, it can be concrete. So, what you find here is, all the so called engineering materials, you could have one technique which provide you the necessary information. So, if you look at composites, they are anisotropic in nature, and if you look at that material equations, they are very complex to handle. On the other hand, if you have to interpret only what happens on an isotropic coating, it makes your life simple on finding out at least the surface strains on composites. And I said, in any technique, material advancement has contributed to the development. So, people have developed coating from rubber to human bone, because the base material controls what should be the nature of the coating, because if you look at composites, they actually reinforce it with fibers, and one of the thumb rules as, if you look at the base material, the reinforcement material should have Young's modulus 10 times that of the base material. This is a thumb rule. Only then the fibers really reinforce the primary material. And here we have seen when I use a glass, it is 70 GPa, which is comparable to the metal. So, it is going to reinforce. On the other hand, if I have a photoelastic coating which is just 3 millimeters, even though it is 3 millimeters, the Young's modulus is only 3 GPa, whereas the metallic this one, if you are aluminum it is 70 GPa and then steel it is 200 GPa, hardly this coating will affect, but even then we have developed correction factors for other reasons. So, what you will have to look at is the greatest advantage of a coating technique, you can apply to a variety of base materials provided you have appropriate coating properties. And now, let us look at extrapolation of whatever we have learnt in transmission photoelastic analysis, and we look at stress optic relations for coatings. And I have already drawn up your attention that both the incident and reflected light contribute to photoelastic effect, because you are seeing the light reflected, and I said for a coating of thickness Hc, because the material what I use is birefringent, it behaves like a crystal when it is loaded. I can also write the stress optic law, wherein I get the coating stresses. Since we are going to have specimen as well as coating, the symbolism used is a symbol C either at a superscript or a subscript indicates that I am dealing with the coating. And when I want to have sigma 1 C minus sigma 2 C, if I know the F sigma of the material, then I can write this as N F sigma by 2 H C. For developing this equation we took about 6 to 7 classes in transmission photoelasticity, because you need to know what is retardation, how it optics related, how the refractive index is looked at as ratios of velocities, how refractive index can be compared to stress tensor, all that we developed. Now, we take that advantage, we take the advantage of that knowledge, and we only look at both incident and reflected light contribute to the fringe formation, and what you have instead of Hc I had to put 2 Hc. But even this representation is not very convenient. See, in the case of photoelastic coating, one of the assumptions I make is I put a coating on the specimen. When I load the specimen, I want to perceive the adhesive is so well bonded that whatever the strain developed on the base specimen is transmitted faithfully to the coating. So, instead of looking at stress optic law, I should essentially look at strain optic law, that is more appropriate, because the way the model is loaded, the way the coating is loaded is different. So, we will have to look at what is strain optic law. So, what I have here is the birefringence in the coating is introduced through the surface deformations at the interface, because we said that the coating becomes temporarily birefringent when loaded. How the loading comes? The loading comes, it is introduced through the surface deformations at the interface. So, in view of this, it is useful to represent the photoelastic phenomena to the strains developed. And strain is also a tensor of rank 2. So, instead of having sigma 1 C minus sigma 2 C, I could also think of writing it as epsilon 1 C minus epsilon 2 C. and I will also bring in a material parameter. There we have said, you must be wondering why I was calling that as f sigma. At that time you would not have noticed why a suffix sigma should be attached to f. I said it is a material stress fringe value. So, following the similar logic, we will have this equation with f epsilon. We will say material strain fringe value, but we will have to find out what is f epsilon, that is a different story. But writing the equation is now much simpler. We follow the same logic, and I write this epsilon 1 c minus epsilon 2 c as n f epsilon divided by 2 h c. The factor 2 comes because both the incident and reflected light contribute to photoelastic effect. So, we call f epsilon is the strain optic coefficient. And epsilon 1 c minus epsilon 2 c gives the principal strain difference in the coating. See, the real utility of photoelastic coating you will see only when this equation is recast comfortably, because ultimately what is it that I want? My interest is not to worry about what are the coating stresses, my interest is to find out the stresses developed on the specimen. So, that is where I have to bring in mechanics of solids. How do I find out the stresses on the specimen based on coating stresses? The coating is birefringent, that is why I call this as the birefringent coating. When the loads are applied, it acquires properties of the crystal, behaves like a crystal, and you have the phenomenon of birefringence and fringes get formed. And there are also many other subtle issues. See, if you look at transmission photoelasticity, we have never discussed how many fringes I will observe in an experiment. We have never even talked about it. Depending on the load applied, you will get so many fringes. If the fringes are less, increase the load. Only when we discuss 3-dimensional photoelasticity, I said I have to calculate the load very carefully, so that at stress freezing temperature the model should be strong enough to withstand, and also how many fringes you have to see on the slices, and you have to do some calculation. As far as 2-dimensional photoelasticity is concerned, there was no discussion on how many fringes I will see. But the moment you have come to photoelastic coatings, we will also have to worry about how many fringes I would normally see in a photoelastic coating test. This becomes an issue, because what you want, many of your engineering components you do not want them to become plastic at service load conditions. You want them to remain only as elastic for various reasons, because if there is a moving parts involved, it has to remain elastic for it to do its function. And another important aspect what you have noticed here is, it is the strains that developed on the specimen get translated to the coating. So, coating is not loaded directly. See, in the case of plastic, if you directly apply the load, you are really applying, because of low Young's modulus, you will also have large strain developed and you will have many fringes seen. But here only the surface strain is transmitted, and surface strain in a service load condition you want to operate much below 2000 microstrain. Even if you say it reaches 2000 microstrain, normally the number of fringes observed in a photoelastic coating test are minimal. And we are also looked at in transmission photoelasticity, most of the time we worry about monochrome light source, and we have looked at the color white light only from the point of finding out the gradient direction, and white light was used as an exception in transmission photoelasticity, in conventional transmission photoelasticity. But with the digital photoelasticity, you have 3 fringe photoelasticity, where you use color for quantitative evaluation of data. that is different. In reflection photoelasticity, because the fringes that you see normally are much less, you generally use white light. Very occasionally you look at a monochrome light source, you look at white light only. So, this is one difference, and we will also have a specific discussion what is the maximum fringe order you can see for a given coating and base material combination. It is dictated by the base material, because when it yields, what way it is going, the properties, elastic properties will influence. So, the number of fringes you see are very small. So, one of the cautions which I used to normally mention is, I have been saying if I have good colors, it is very interesting and motivating for you to work. Photoelasticity offers that benefit, but in reflection photoelasticity, if you see colors, it is a warning signal, the specimen is heavily loaded. So, you should not get enamored by the colors, you should really take corrective measures and then improve your design. These are all like thumb rule type of thing, okay, depends on various factors, but you will have to keep in mind, if you do not see colors, be happy about it. If you see colors, you will have to worry about it, but if you do not see colors, the problem may be the coating may have got peeled off. If you do not bond it, in all the coating techniques, you have to follow the supplier's recommendation. Whoever is supplying you the adhesive, he will give you a recommendation, what is the surface preparation, what is the curing cycle, what is the kind of pressure applied, all that you should follow faithfully. If you do not follow that faithfully, the strains of the specimen would not be transmitted to the coating. So, this is one issue. Even if the strain is transmitted faithfully, the number of fringes normally observed in a photoelastic coating test are generally smaller. And we also define a factor called the strain coefficient K. This is very similar to what you have seen in transmission photoelasticity. In transmission photoelasticity, you had defined f sigma as lambda by capital C. Here it is defined as f epsilon is defined as lambda by k, and you have to recognize that retardation introduced is a function of wavelength lambda. So, now you have the definition of f epsilon. F epsilon is related to lambda by k, k is the strain coefficient, it is supplied by the manufacturer or to be determined by calibrating the coating. This is also a subtle difference. In normal transmission photoelastic analysis, you do not handle capital C, you only evaluate f sigma, and many of your calculations you do with f sigma. And I have already said that arithmetic in transmission photoelasticity is very simple, only the conceptual understanding is little involved. The same applies to reflection photoelasticity also, arithmetic is very simple. Instead of finding out f sigma or f epsilon, we would find out what is k. By calibrating the coating material, you essentially find out k. And I also said photoelastic coating can be applied from a range of material from rubber to high strength steel, and rubber has a very low Young's modulus, and if I have a coating material that should have much lower Young's modulus, so that it does not reinforce the surface of the rubber. So, in those applications it may be prudent to directly take a tension specimen and pull it, which is made of the coating material, and find out f sigma. From there you find out k. Ultimately you want to have k. Finally, we are going to develop an expression involving sigma 1 s minus sigma 2 s as a function of the fringe order observed and also the thickness of the coating and elastic properties of the base material will come, that is will be the final expression. And what you need to see here is k is much more fundamental in the case of photoelastic coating. And what is interrelationship? Because we all deal with isotropic material. For a perfectly linear elastic photoelastic material, one can find an interrelationship between the parameters f sigma and f epsilon, which is straightforward. It does not require any great mathematical skills. I can find out f epsilon as 1 plus nu c divided by E c into f sigma. So, what it shows is, if I find out f sigma, I can find out f epsilon. If I find out f epsilon, I can find out f sigma from this interrelationship, and that is what I said when I have to go and find out the calibration constant for a coating that is to be applied on rubber. Finding out f epsilon may not be practical, finding out f sigma is more practical. You take the coating material, make a tension specimen and pull it, find out f sigma, find out what is the f epsilon from this interrelationship. Once I know f epsilon, I can also report it what is the value of k, because I know f epsilon equal to lambda by k. And another basic observation is, why do you want to have a thick photoelastic coating? See, I said number of fringes you generally see in a photoelastic coating test is small, and if you want to apply any coating, it should be as thin as possible, is desirable from analysis point of view. But from practical consideration point of view, I must see some fringes. If I do not see some fringes, how do I make measurement? And there are also developments. See, the digital imaging hardware has also influenced photoelastic coating test. What I could not perceive with human eye, I could do a very refined analysis with digital photoelastic technique. So, that also says I can go for a thinner coating. If I go for thinner coating, it is always advantageous. My mathematics becomes very simple. If I go for a thicker coating, I do not give up, but I bring in correction factors. That is how engineers operate. Correction factors are part and parcel of reflection photoelasticity. Even for simple calculations, you have to bring in correction factors, but it is an engineering tool and has been solved for a variety of problems. Assembly stresses, see, you must have seen in several towns, they now put this central lighting. You have a huge pole that is put and you have a lamp on top of it, and if you go and look at how this lamp post is clamped to the ground, you have thick bolts, and that had assembly stresses problem, and this was sorted out by performing a photoelastic coating test. Now, it is a well proven design, but when the initial design was developed, by tightening those bolts, you had developed assembly stresses, and eventually the failure of that pole was because of stresses introduced during assembly. See, assembly stresses, how do you model analytically? You can't model it easily, it is so difficult, and photoelastic coating came to the rescue. And another instance where photoelastic came to the rescue was in the analysis of rudder of a Concorde aircraft. The rudder was failing repeatedly, and what they found was they had done a finite element analysis, they had also done a strain gauge analysis. The design was based on strain gauge analysis, but still the rudder kept failing, and strain gauge is a point by point technique. Then people decided, why not apply a photoelastic coating on the rudder. When they took the measurement, they found the location of the strain gauge was slightly away from the maximum stress zone. So, it was only reporting 75% of the stresses. So, you had an error in strain gauge value, because it is shifted away from the main point of interest. With photoelastic coating being a whole field technique, they could use that information and redesign the rudder, then it had a fairly a good life. So, if you look at photoelastic coating, it is a very industry friendly technique. Like I said, it is only a tool, you should know how to employ the tool correctly. So, for those assembly stress problem, what you have as light poles, photoelastic coating helped, and many engineering applications you find. So, you want to have sufficient optical response in a photoelastic coating test. If the coating thickness is increased, you get sufficient optical response, but when the coating thickness increases, interpretation becomes difficult. So, you have to have a trade off, you have to have a compromise. So, that is part and parcel of engineering, and you will see in the correction factors what we will find out is they will say that you put a coating of reasonable thickness over the material over the specimen, find out pockets of stress concentration, then peel off this coating and put a thinnest coating possible, because in a stress concentration I already have sufficient stresses to develop sufficient number of fringes. So, this is how they handle the problem from engineering sense. Coating thickness is a nuisance, but without coating thickness I cannot see the fringes. So, identify pockets of high stress concentration, then redo the analysis with a thinner coating. Now, we will look at what is the mathematics behind it, because the focus is evaluation of coating and specimen stresses. And we have to make an assumption, without assumption we cannot proceed. Are we satisfying all the assumptions in the coating testing is what we have to examine. And just now I said the thickness should be sufficient for me to see fringes, but when I do the analysis I want to claim the thickness of the coating is very small. So, this is the assumption that I make, and I said do not think when I make assumption we are making a crime, it is not so. I have pointed out that when the Young's modulus of the coating material is much smaller than the base material, even though the thickness appears considerable, it really does not reinforce. In certain class of problems it affects, in certain class of problems it is not a very serious mistake. So, the thickness of the coating is very small, and I said in all the experimental methods Poisson ratio will be a nuisance, and here you assume both the specimen and coating have the same Poisson's ratio. And you know polycarbonate we have seen, polycarbonate material property we saw, it has a Poisson ratio of 0.28, many materials have 0.25, 0.26, all this metallic materials, and this is much closer, and polycarbonate is a very popular coating material in photoelastic coating also. So, second assumption also can be reasonably satisfied. The third assumption is the specimen and the coating are in a state of plane stress, that also can be easily satisfied, it is not a difficulty. And what do we see? And we also have a very nice way of looking at it. I have this as a prototype that is given in a gray shade. On the prototype I put a coating at a place of interest which is large enough, and I take a small elemental element which is shown here, and I have a full freedom to select my axis at the point of interest. So, to minimize our mathematics, I take an axis along the principal stress direction 1 and 2, and they also in isotropic material coincides with principal strain directions, and I take the thickness as the direction z. And imagine this coating is very large enough, this is not because it is a small place, it is represented, the representation is I have a prototype of some thickness on which a coating is put, and I am looking at a small elemental area where I have a coating as well as the specimen. And what is the important assumption that I make, which I have already mentioned it, I have a adhesive which is good enough such that the surface strains of the specimen are transmitted to the coating through the adhesive without loss or amplification. And what I have on the coating, I will have a strain epsilon 1 c, which is a function of x comma y. I will also have the strain epsilon 2 c, because I have taken my axis of reference along the principal strain directions. And if I have to say the surface strains are faithfully transmitted, what do I mean physically? I physically anticipate the strains in the coating and the strains in the specimen are identical. For a moment we close our eyes on mismatch of Poisson ratio, but we have started the assumption both have the same Poisson ratio. So, that does not, whatever happens to the specimen happens to the coating also. If there is a mismatch in Poisson ratio, I have to bring in a correction factor. This is what I said. While developing the basic equations, we make certain assumptions, but when we actually put the methodology in practice, I violate some of these assumptions because of exigencies in the experiments, but I improve upon my results by bringing in correction factor. So, what I am going to have is, I assume epsilon 1 c equal to epsilon 1 s and epsilon 2 c equal to epsilon 2 s. This is what I am going to have. And what I have here, I have already mentioned, when I have a superscript or subscript with c denotes coating and s denotes specimen. In all our subsequent discussions, we will have that symbolism followed. And what is my ultimate goal? My ultimate goal is, I have to find out the coating stresses and specimen stresses. How do I go about? I am just going to make a beginning of it, and then later you do the development at home and come back for the next class. So, I can look at the stress strain relations, and which you know very well. When I am also looking at a plane stress situation, I can write epsilon 1 s simply as 1 by E s sigma 1 s minus nu s sigma 2 s. These are all very well known equations. Epsilon 2 s as 1 by E s into sigma 2 s minus nu s sigma 1 s. On similar lines, I can also write epsilon 1 c epsilon 2 c in terms of coating stresses, and now we have the basic assumption epsilon 1 c equal to epsilon 1 s, epsilon 2 c equal to epsilon 2 s. Now, you have strain stress relations. What is the next step? You can find out the coating stresses as well as specimen stresses from all these quantities. I have this epsilon 1 c like this, and what I want you to go to the room and then work on this is, what is the expression for sigma 1 c and sigma 2 c. It is fairly simple and straightforward. Take it as a home exercise. When you come for the next class, give me the expression for sigma 1 c and sigma 2 c in terms of the Poisson ratio of the coating, specimen, and also the specimen stresses. And these expressions will be same when I go and see brittle coatings. In brittle coating, we will handle them individually. In photoelasticity, what do we get? We always get only principal stress difference or principal strain difference. That is where the whole thing changes. So, in this class, what we have looked at is, I said photoelastic coating has made application of photoelasticity to industrial problems very attractive, and I said it is a very nice engineering tool, and approximations start right from data recording, because in transmission photoelasticity we wanted normal incidence. We maintained that even in 3 dimensional photoelasticity. Even if I analyze a 3 dimensional model, though I have not mentioned it explicitly, I may immerse it in a liquid which has the same refractive index, and then when I put the ray of light, it will still retain a normal incidence, though the model is complicated shaped. The moment I come to reflection photoelasticity, because I have to look at the reflected light, I compromise on normal incidence, and in order to simplify that or minimize that whatever the error introduced, one of the requirement is I keep the polariscope far away from the model, so that I reduce the angle of oblique. Then we looked at what is strain optic relations, and I said what is the interrelationship between f sigma and f epsilon. Then we moved on to look at how to find out the specimen stresses, and specimen stresses you have to find out first from coating stresses, determine the coating stresses, from coating stresses go on to specimen stresses. And what is the basic assumption? The strains are faithfully transmitted, and you will have to go and get me the expression for sigma 1 c and sigma 2 c. It is very simple arithmetic. If you do it at your rooms, your preparation for examination becomes very simple, and this is fundamental for any of the coating techniques.